First meeting, first topic. For the final period, we have functions and their graphs. So we do have this topics, the relations and functions, the vertical line test, the domain and range, evaluating functions, types of functions, combination of functions, and then composition of functions. So for day one, what we're going to discuss is from numbers 1 to 3. Okay. So the relations and functions, this is actually part of the general mathematics, the one that you had in your senior high school. So I hope that you can remember it. Um, when we say relation, so a relation is actually between two sets, X and Y. So it is a relation that is actually a set of ordered pairs, each of the form XY, where X is a member of X and Y is a member of Y. So when we say ordered pairs, so for example, if we have the set X, okay, if we have set X which is has the elements A, B, C, D, and then we do have set Y that has the elements 3, 5, 7. So we can have a relation, okay, a relation if we do have say we do have a set G, and then we're going to have a pairing of elements from X and Y. So for example, we do have the ordered pair A and 3. Okay, then we do have another ordered pair, C and 5, and we have, for example, B and 7. So as what you can see, G is a relation because it is a set of ordered pairs in which the ordered pairs are from the elements are from X, okay, from X and from Y sets. Okay. Um, so to continue, so I will be deleting the writings on the screen. So we also have a definition for the function. So a function from X to Y is a relation between X and Y that has the property that any two ordered pairs with the same X value also have the same Y value. Okay, so continuing, if we do have X and Y, the variable X is the independent variable and the variable Y is the dependent variable. So what do we mean by this? Okay, so if for example we have the function or say an equation y equals to 2x plus 1. Okay, so this is an equation, and if you can still remember, so we do have the what we call as the table of values. The table of values, so you put here your x, you put here your y, then you're just gonna complete the table. So say you do have here a value for your x, so the value of the x will be coming from you. Okay, so if you want this to be 1, you want this as 2, 3, so on and so forth. Okay, so depending on the value of your x, so you can have a value for your y. How will it be? Okay, or how will it happen? So simply you're just going to substitute 1 to the x here. So that is 2 times 1 plus 1. Okay, so that is 2 times 1 plus 1. So we do have here 3. And then this 2 here, also substitute it here so that you can have a value for your y. So that is 2 times 2. We do have 4 plus 1, so that is 5. And then this value of x here, which is 3 again, you're going to substitute it here. So that is 2 times 3. So it is 6 plus 1. We do have 7. Okay. So what does it mean? So um, with the x, okay, being the independent, so it means that just like this table of values, so you would notice that we assign values for x. Okay, x can stand alone. So x, this is actually independent. And then the value of y, it will depend on the value of x. So that is the reason why we do say that y is a dependent variable, because with a value of x, therefore we can have a value for y. Okay. Next, so continuing, so with the previous slide, so we do have there the definition of relation and then function. So a function is a relation defined as set of ordered pair x, y, where no two or more distinct ordered pairs have the same first element. That is, every value of x corresponds to a unique value of y. Okay, so it is said here that a function is a relation if no two, okay, if no two or more ordered pairs have the same x element. Okay, so if we're going to list, for example, we do have relation. Okay, we do have relation example. So the example of relation, so say um we do have set A. So set A has the set of ordered pairs. For example, we have -2, 0, then say 1, 3. We do have 4, 3. Then we do have say -1 and 1. Okay. So as what you can see, this is this is actually an example of relation because we do have pairing. So we do have here ordered pairs. Okay. So we have the x values, then we do have the y values. Okay. So this is a relation. Another, so another example of relation, so just like in the table of values, so if we have the table of values, so considering y equals to say for example, so 2x plus 1, so we have x and then we have y here. So if we do have a value for x, so say we do have here -1, 0, 2. So these are just examples of x. And again, remember that the value of y will depend on the value of x. So if we have -1 for x, so you substitute it here in this equation. So 2 times -1, so that is negative 2 plus 1. So we have -1. Okay. Then if we do have 0 here as our x, so 2 times 0 is 0 plus 1. So it is 1. And then 2 for x, so that is 2 times 2 plus 1. We do have here 5. Okay. So you can try to check. So 2 times -1 again, because -1 is the value of x here. So we do have here -2 plus 1. It is -1. So the value of 0, substitute it here again. So you're gonna have a value for your y. So you have positive 1. And then when your x is 2, so that is 2 times 2 plus 1, we do have 5. Okay, so in terms of ordered pair, we can also list this. So say for example, we do have set B. Okay, if you would like to test this, so you're gonna see pairing again. So we have here -1, -1. We have here 0 and 1. And then we do have 2 and 5. Okay, so still we have the x values -1, 0, and 2, and we do have the y values -1, 0, and -1, 1, and then 5. That's it. Okay, so these are actually examples of relation. And then when it comes to functions, so when we say a function, so there should be no, so just remember this, no repetition of x values. Okay, so when we say no repetition of x values, the value of x, so there shouldn't be the same values of x in a set of ordered pair. So for example, in this relation A, so as what you can see, so we have -2 for x, 1, 4, and then -1. So as what you can see, no x was repeated, no value of x was repeated. Therefore, we can say that this relation, okay, this relation is a function. Okay, so this is a function. Another, so let us take a look at our relation, the B, okay, set B. So we have the value of x, the value, so -1, 0, and 2. Again, there's no repetition of the value of x. Therefore, we can say that this is a function. So this is showing you that a relation can also be a function. Okay. But then there are instances that a relation cannot be a function. Of course, if there will be repetition of x. So I will be clearing the screen. So for example, if we have C equals to the set of ordered pairs, say 3, and then -1, we do have 4, and then 3, we do have 2, and then say we do have -5, and then we have 4, then 0. Okay, so if you try to check the x, okay, these are the x values. As what you can notice, so we do have 3, 4, 2, and 4. So 4 was repeated. So in this case, so this is a relation, but then this is not a function. Okay, so you have to take note of this, that if you do have ordered pair, so we can say that it is a relation. So whenever you see a set with ordered pairs, it is actually relation. But then if you will be asked if it is a function, so what you need to do is to check the values of x. If there is no repetition of the value of x, therefore the relation is a function. If there is a repetition or there are the same values of x, therefore the relation is not a function. Okay, so you can also see references in which when you read about function, so you can actually you can see there that it is mentioned no repetition of abscissa. Okay, so when we say function, so no repetition, no repetition of abscissa. So the word abscissa, we already made use of this last midterm, in which when we say abscissa, we are only referring to the x value, um, and in which the y is the what we call as the ordinate. Okay, so you can also see no no same abscissa. So that is for the function. Okay. So let us go back to the PowerPoint. A function is an equation that has only one answer for y for every x. And a function assigns exactly one output to each input of a specific type. So here, um, so it is said that function has only one answer for every x. So for every x, so remember that x shouldn't be repeated. So if we have exactly one value for x, so there will be an answer for y. And when it comes to the terms here, output and input, so this actually pertains to the y and the x. Okay, so remember that when we say x, so this is our independent variable, and y is the dependent variable. So again, if we do have the equation y, okay, for example, y equals to the 2x plus 1. So this is the equation. So if we are going to consider the input, so input and then the output, actually in between these two we do have the process. So when we say input, so we're referring to the x, okay, and output is the y. And then lastly, the equation to I do have x plus 1 equals. So in that we do have the input of like 2. Okay, so with the process you're going to substitute 2 here, so we have 2 times 2 plus 1, so our output will be 5. If we have here 4, so that is 2 times 4 plus 1, so we do have 9 as the output. So that is what we mean by the output and input here. So assign exactly one output to each input. So it is also the same as saying having one answer or one output to each um, x, okay, for every x, in which every x is what? It is the input in this equation. Okay. Um, I will be removing the ratings. Okay. So this is identifying if the following equation is a function or a mere relation. So there will be given equation. So we're gonna identify if it is a function, or if it is not a function, it means that it is only a relation. Okay, it is only a relation. So just remember that we do have relation if there is a set of ordered pairs. Okay? And the set of ordered pairs, the relation, you can classify it or you can identify it whether it is function or not. So if a relation is a function, so you're gonna tell that it is a function. If a relation is not a function, because there is repetition of x, therefore the answer would be mere relation. That is for this set of questions here. So in example number 1, so as what you can see, so we do have here relation. Okay, but we need to determine if this relation is a function. So what we need to do? So we need to check the x values. So we have 0, 2, 4, and then 6. So 0, 2, 4, and 6. So it is very clear that there is no repetition, repetition of x values. Okay, since there is no repetition of x values, therefore we can say that this is a function. Okay, so this is a function. That is the answer. Next. So another one, so we have x of 1, negative 3, 6, and negative 4. So you have to take a look. Actually, this is negative 3 and 5. Okay, that is a comma. So we have the x values 1, negative 3, 6, and then negative 4. So again, there is no repetition. If there is no repetition of x, therefore this is again a function. Okay. Next. So this is an example of a diagram. So in this diagram, we do have the names of the daughters and the names of the mothers. I hope that you are familiar with the term domain and range. So when we say domain, so this is actually the x, okay, and range is the y. So as what you can see, so we do have the daughters Ami, Anna, Jocelyn, Daphne, and then Jenny. So no two daughters, okay? No, for example, um, Ami, okay? Ami is the daughter of Mrs. Smith. But then Amy is not the daughter of Mrs. Sanchez and Mrs. Perry, only by Mrs. Smith. The same with Anna. Therefore, Amy and Anna are siblings. But then take a look. So Amy, there's no um with the name of Amy, there is only one arrow. Okay, one arrow. So this means that for Anna, one arrow only. Jocelyn is also one arrow. Daphne also one arrow. And then Jenny is one arrow. So we can say that there is no repetition. No repetition of X or domain. So therefore, we can say that this is a function. Okay. Next. So with this set x, so let us take a look at the x values. So we have x of 9, a, negative 9, negative 9, and then we have 9. So as what you can see, so we have here the same x value of 9. So we have 9 on the first ordered pair and also 9 on the fourth. So since there is repetition, okay, repetition, there is repetition of x, then we can say that this is not a function. If it is not a function, therefore we can say that this is a mere relation. So I will be deleting the writings on the screen. Okay, so the next example is set F, and we can see here the the set of ordered pairs. So we have we have the x values of 1, 2, 3, and 4. So it is very clear that we do not have repetition. So no repetition. No repetition of x. Therefore, we can say that this is a function. Okay. Next. This is again a diagram. So in this diagram, so we do have domain of x and then range the y. So as what you can see, with each element on x, so there's only one arrow for each. So again, no repetition of x or of domain. Then we can say that this is a function. Next. A relation may be expressed through ordered pairs, table of values, equation, graph, or through a diagram. So with the examples that we do have a while ago, so we already have examples of this. The ordered pairs, the TOV or table of values. We also had equation as well as diagram. For the graph, actually, we're going to have the graph under the vertical line test. So just to show you that a relation can also be in a form of graph. In the vertical line test, so if there is a vertical line that crosses the graph twice, okay, if we do have a vertical line crosses a graph twice or more than twice, then we have 2 points with the same first x coordinate or with the first or x, okay, first x values, or simply we can say same x values, but different y coordinates. If this is the case, okay, if the vertical line crosses the graph twice or more, then we can say that it is not a graph of a function. So we can say that it is not a function. So just to make it simple. Okay. So we have your examples. So in this figure, so it is said here that a line, okay, we do have here a line, and this line is actually a function. Okay, it is said to be a function. Because if we're gonna draw here, okay, so if we're going to draw a vertical line, okay, that crosses the this line, as what you can see, it crosses the graph only once, okay, only once. If it crosses the graph only once, we can say that this is a function, okay. If ever that the vertical line will cross the graph twice or more, it is not a function. Another example. So it is said that this is a graph of a function. So this is a function. So as what you can see, this is actually a curve. Okay, a curve. And if you're gonna draw a vertical line here, possible you might say that it is not a function because possible that there can be two or more points in which the vertical line crosses. By the way, since this is a curve, you can actually try to make this image of this curve bigger. So when you try to zoom it, so you would notice that there's no there are no points that are arranged vertically on the same line. So what do I mean by that? So if ever that you're gonna have a curve, for example, this is your curve, and then your curve um has a line like this, okay, then it became a curve again. So if originally your graph really has a line, okay, really has a line. So if you're going to put a vertical line here, so in that case, because this is a line, if this is a line, therefore this is not a function. Because if you do have a line, so you would notice that the vertical line will really what? Will really cross all the points here. Unlike this one, this is actually a curve. So there's no line here. Okay, there's no line here. So try to zoom it and up, well, if you can make it more big, so you would see that it's still a curve. Okay, and therefore it is really a function. Next, so only one point will have an intersection with the vertical line if we do have a curve like this one. Okay, so number 3, we do have here parabolas. Okay, so this one is a parabola. This is a parabola that opens upward. And then the other one, we do have here a parabola that opens to the left. It opens to the left. Okay. By vertical line test, you can easily identify which one is a function and which one is not. So by vertical line test. So as what you can see, the parabola that opens upward, the vertical line crosses the graph only once. Okay, only at this point. Therefore, we can say that this is a function. And then the parabola that opens to the left, so if you're going to draw a vertical line here, it is very obvious that the vertical line touches the graph twice. Okay, it touches the graph twice. So if that is the case, we can say that this is not a function. This is not a function. Because as what you can see, if you still remember your Cartesian plane, okay, in the Cartesian plane, we have the x-axis, the y-axis, and we do have here, values of the x. Okay, values of the x. So this is -1, -2, -3, -4, -5, -6. On the right, we have 1, 2, 3, 4, 5, 6. On the upper portion, we have 1, 2, 3, 4, 5, 6, 7, 8. On the lower, -1, -2, -3, -4. Okay, so on and so forth. So you can try to determine the coordinates of this point. Okay, as what you can see, these 2 points have the same values of x. So what would it be? So if this is -1, -2, so this is at -2.5. And then for y, so we have 1, 2, 3, 4, 5, 5.5. So coordinates, our x is -2.5, -2.5, and then our y is 5.5. So if you try to determine the coordinates of the second one, so the same, -1, -2, -2.5, and then, so y, so -1, -2, -3, -4, -4.5 here. Okay, -4.5. So if you notice, so we do have the same values for x. So it means that there is repetition. There is repetition of x. So there is repetition of x value. Therefore, we can say that this is not a function because there is repetition of negative 2.5. Okay. Next. So this is also a function, but then what is the reason? Okay. So if we try to draw again a vertical line here, okay, if we try to draw a vertical line here, so it crosses the graph once in this portion. If you are going to draw a vertical line here, okay, so you would notice that there is the presence of halo. When we say halo, this is not included. Okay, it is not included. If it is not included, if there is a vertical line, therefore, it won't cross anything. Okay, it won't cross anything because there's no part of the graph there because it is hollow. And then when it, when it crosses, so the vertical line crosses this shaded portion, so the shaded portion, this is included. So we can say that the vertical line crosses at this point. So we can say that this is a function. It is also the same when we're gonna have the vertical line here. Okay, next. So when it comes to the domain and range, the domain D of a function can be, I'll just like to correct it. So it is can be defined as the set of all x coordinates in the set of ordered pair, while the set of y coordinates is referred to as its range. So again, the domain is the set of all x coordinates, and for range, we do have the set of all y coordinates. Usually, the elements of the domain and range of a function are written in increasing or decreasing manner. Okay, so if you are going to identify the domain, so the elements should be arranged in increasing and decreasing order. The same with the range. So identify the domain and range of the following functions. So we have here number one. So given a set A with ordered pairs 1, 3, 2, 4, and 5, 5. So simply you're just going to list. So the domain, so you're just gonna list so all the x that you can see in the ordered pair. So we have 1, 2, and then 5. Okay, so D has the elements 1, 2, and then 5. And then for the range, so we have all the y's here. So we have 3, 4, and then 5. Okay. Next. In the second example, so given S, so the same thing that we are going to do. So we have to identify the domain of this. So we do have 6, 5, and then 3. We have 6, 5, and 3. So as what you can see in the first number, so the domain and range are already arranged in increasing order. In the second number, the domain is arranged in decreasing. So this is okay. And then the range. So we have 3, 3, and 3. By the way, if you can remember the rule for sets, if there is a repetition of element, okay, in listing it, so you're just gonna write it once. So we have 3, 3, and 3. So simply the range is 3. If there is repetition. Next. The third, so we have this table of values. So this is a TOV. So you're just going to list again. So we have the X. So we have here the domain. So we have -4, -1, 3, 6, and then 9. -4, -1, 3, 6, and 9. And then for the range, so let us take a look at the table of values. So we have 16, 1, 9, 36, and 81. We can possibly arrange it. So starting with 1, followed by 9, 16, 36, and then 81. Okay, so in increasing order. So again, we have 1, 9, 16, 36, and 81. Okay. The next slide, we have the fourth. So this is actually a diagram. So with this, again, so in the first one, so we do have here the domain, and then we have on the second one, the range. So we can just list it. So the domain, so in order, so we have 1, 4, and then 5. And then the range, so we have 2, 3, and then 6. Okay. Next. So in this slide, so you can see here examples of functions. If you see an example or a given in this kind of format, so you can just take note of what can be the possible domain and range. So in the number 5, okay, in number 5, we do have y equals to 2x minus 3. This 2x minus 3, this is actually an example of a line. And if we do have line, so the domain is the set of real numbers. This one, we do read this as x such that x belongs to the set of real numbers. So that is how we are going to read it. Okay, x such that x belongs to the set of real numbers. The same with the range, y such that y belongs to the set of real numbers. When we say set of real numbers, it can be any number. So you can have 0, you can have negative, you can have positive, you can have fraction, decimal, so any number. Okay, next. So I will be clearing the writings. Um, Next, we have a function. So this is actually absolute. So y equals to the absolute value of -2x. So this is an absolute function. And if we have an absolute function, so the domain is again the set of real numbers. And then when it comes to the range, since this is absolute, so it means that whatever number you substitute for x, knowing that it is absolute, so your y will always be what? Will always be positive, and it can sometimes be equal to 0. So in that case, we can say that y such that y is greater than equal to 0. Because again, it will never be negative because the function is absolute. Next. On number 7, so we have this f of x equals to 4x squared. So the f of x, this is also the same as y. Okay. Um, in this case, so the right side is 4x squared. In this format, so the domain is the set of real numbers. So we can substitute any number for x. Okay. As what you can see for the range is greater than equal to 0. Why is it? Because since the x here, okay, since x here has a square, okay, whether the value of your x is negative or positive, squaring a negative number is positive. Squaring a positive number is still positive. Multiplying it by 4, still positive. Okay, so it means that the range will always be positive. And it can also be equal to 0. How? When your x is 0, so 0 raised to 2 is 0. So 0 times 4 is 0. So that is why range can be greater than equal to 0, or y such that y is greater than equal to 0. Next, number 8. So we have here radical function. In this radical function, so it is said here that we do have x such that x greater than equal to 0 for the domain. So how did it happen? So if you do have a radical function, you take a look at the number inside the radical. And you are going to write it with greater than equal to 0. Okay, that is what you are going to do if you have radical in determining the domain. And then what you need to have x alone on one side. So we have x greater than equal to 0. So it means we're going to divide both sides by 6. So dividing both sides by 6 because you need to have x alone on one side. So canceling, so we have your x greater than equal to 0. And this is actually your domain. For the range, so the range is greater than equal to 0 also. Um, it will never happen that it will be negative, okay? Because since this is radical and knowing that you do not have a negative before the radical sign. So this is actually positive. Unless you see a negative before the radical sign. So that's the time that you can consider negative in the range. Next. So I will be removing the writings. Number 9 is actually an example of rational. For rational, in determining the domain, again, you have to, well, what you need to do is to take a look at the denominator. So for the denominator, what you're going to do here is you have to copy it and then write not equal to 0. In the rational a while ago, what we did, we copy it, okay, and then we write greater than equal to 0 because this is radical. For rational, this is what you are going to do, okay? And then just have one side, just have x on one side. So in this case, we're not going to do anything anymore because x is already on one side. So this will be your domain. So this one. So what does this mean? So the domain is x such that x belongs to the set of real numbers except 0. So it is also the same as saying x not equal to 0. Okay? And then for the range, since this is rational, okay, since this is rational, um, for the reason that x cannot be 0, okay, that x cannot be 0, and actually if you try to do trial and error here, so substituting values, for example, um, your x is -1, -2, or it is 1, 2, 3. So there's no possibility that you can have a value for y, or the f of x, or the range be 0. Okay, so that is the reason why it is not equal to 0 also. Next. So for number 10, we actually have here quadratic function. For quadratic function, the domain and the range are both, well, belongs to the set of real numbers. If we do have quadratic of this format, so we have x squared and then minus 5. Okay, so if the format is like this, so um, the set of real numbers for both domain and range. And then for number 11 is also rational. Or rather, this is radical. Radical. We do have the radical sign. So this is radical, same as number 8. Okay, they are the same. So what you have to do here is also consider the one inside the radical sign. So x plus 3, you're going to copy it. And then greater than equal to 0. So again, what you have to do here is you need to have x alone on one side. So here is the x. So you have x greater than equal to 0, and then the positive 3, you can transpose it to the other side. So you can have -3. So simplifying, this is x greater than equal to 0 minus 3. So that is -3. So that is the reason, okay, why we do have this domain. So x such that x is greater than equal to -3. And then for the range, so less than equal to 0. So this time, the radical already has negative. Okay? So it means that whatever number you have here in this portion, um, so because this can be 0 or positive, this portion. So knowing that you have a negative here, so automatic it can be 0 or negative. So therefore the range is less than equal to 0. So for number 12 is also rational. This is the same as number 9. Okay, so what you need to do here again, so you have to consider the denominator. So the denominator is x minus 1. So since this is rational, it should not be equal to 0. So denominator should not be equal to 0. And again, so what you have to do is to what? You need to have x alone on one side. So not equal to 0. The -1, you can transpose it. It will become +1. Okay, therefore, we or with this, then we can have x not equal to 0 plus 1 is 1. So that is the reason why we have this domain. So x such that x is, well, does belong to the set of real numbers, except 1. And then for the range, not equal to 0. So the same as this one also. Okay, so if you try to notice, what is important here is if you do have radical, so you have to take note to write the one inside the radical sign, okay, greater than equal to 0. If your if the x has it has with another term like a number or a constant, so you have to transpose or move the constant to the side where 0 is, and then just have x on one side alone. So just like this number 11. If the function is rational, so just like number 9 and number 12, so what is important is you have to take note of the denominator and making it not equal to 0. So the same if the x in the denominator is together with a term that is a constant, so you have to transpose it to the other side together with the 0, and then leaving x on one side alone. Okay. And then you also need to take note of the prefixes, okay, for the radical, because on the prefixes in the radical, so it is where you are going to base your range. So you can have greater than equal to 0 if you do have the positive radical, and less than equal to 0 if you have negative. When it comes to the rational, so both are not equal to 0. On the next slide, so this is only a summary, okay? The summary of domain and range. Kindly familiarize yourselves with this. So as what you can see, so if we have a function of x, so say we have y equals to k, okay, and k belongs to the set of real numbers. So this is saying that k is a number. So the domain is the set of real numbers, and the range is the k itself or the number itself. If we do have a line, so if we have a line, so the domain and the range is the set of real numbers. Actually, this summary of domain and range, it is also the content of the examples a while ago, which I explained. If we do have quadratic, okay, these are both quadratic. So you have to take note of the coefficient, okay, the coefficient of x squared when the coefficient is greater than 0, okay? So, for example, the coefficient of x squared is, say, 1, 2, 3, okay, greater than 0. Automatic, the domain is the set of real numbers, okay? For the range, so what you have to do is to write this. So, set of real numbers, y greater than equal, and then you have to consider this formula, so 4ac minus b squared over 4a. Where are you going to get the values of the a, c, and b? So it will be coming from here, the a, b, and c. You're just going to substitute it here. And if you're gonna have a number here, okay, after substituting, then that will be included in this range also. So y is greater than equal to that number. The same with a quadratic in which the coefficient is less than 0. So if the coefficient of x squared is negative, the domain is also the set of real numbers. And then this time for the range, it is the set of real numbers, and then y is less than equal. Again, you have to substitute the a, b, and c here so that you can come up with a number in this portion. So y is less than equal to that number. Then here we do have here rational. So I already explained this a while ago. If we are going to have a rational function, so what is important is the denominator. So you're going to copy it, okay, not equal to 0. So it is here. And so not equal to 0 also for the range. Then if we do have radical, okay, these are both radical. When the index of the radical is odd or even, so you have to follow this. When the index is odd, so the domain is the set of real numbers as well as the range. If the index is even, for example, you have fourth, uh, the fourth root, the sixth root, or the square root. So we do have the set of real numbers for domain, and then the function is greater than equal to 0. Then for the range, so set of real numbers, and then y is greater than equal to 0. So this is the summary of the domain and range. So that ends this lesson. So thank you.